So Adrian, can you hear me?
Can you hear me?
I can hear you.
Good.
So how much do you disagree with what I said?
I know I agree with most of what you say. We're not quite aligned on the role of real numbers in classical physics, but
So we'll
yeah.
pick up on those points.
Okay, very good.
We will pick up on those points of disagreement.
Very good. We're not going to fight because he is too far away.
So you will have to then come. So I will call the names one by one, and I request people to say from where they are, which institutes. Name I'm saying. So first one is Sukalyan Bhattacharya. Can I have the mic over there?
I am from Texas Tech University. My question is, do you consider, it is for Professor Gisin, do you consider the device independence of individual subatomic measurements to be axiomatic? It seems like yesterday you were sort of saying in that line, if I'm not mistaken, and today you didn't mention anything about device dependence. So is that axiomatic to you?
So device-independent quantum information processing, and by the way, Adrian, myself, and many more worked on that since the beginning, assumes very clearly, so this kind of black box picture. So what do we assume? It's not that we assume nothing. It's said always device-independent, but we still assume that you have a classical input that we can control, we the humans, and also that there is a classical outcome, and that we also can collect these outcomes, and we know that this outcome is coming from Alice box or Bob box and so on. So there is this little assumption that indeed measurements have outcomes, and that the outcomes are accessible to humans. And of course, humans can delegate that to a classical computer to store the results and do the statistics and all that. So in this sense, there is a bit of some minor assumption about measurements in device-independent quantum information processing. Now, you may call that axiomatic if you like, but it's just common sense.
Just a follow-up question. So let's say I have a hidden variable, and a certain device actually is dependent on that hidden variable. The outcome is, so you will get an outcome. That's foregone conclusion. But your outcome would be dependent on the interaction of the device and the hidden variable. Is it a possibility, or you see a no-go upfront?
No, you can have indeed hidden variables. Bohmian mechanics is an example. But then, we assume there are a few assumptions when you do this device-independent quantum information processing. Clearly, you need, depends now, there's a large variety of device-independent quantum information processing, but usually the standard thing is you assume a Bell inequality violation, and hence you exclude local variables, and that's the way you exclude, for instance, the kind of variables you have in Bohmian mechanics.
True. However, means in order to do that, to exclude the local variable, there is possibility that if there is some kind of dependence between the device and the local variable, then basically that exclusion is not a priori correct.
No, but that's okay. If there are local variables, these local variables can influence the outcome of the measurement. That's not a problem at all.
Okay.
Maybe, we move to that.
So you can discuss more with him. Now, I request Orijit Chatterjee. And tell which institute are you from, and you
Hi, I am Arijit from ICER Pune. My question is on that stochastic Schrodinger equation that you showed. There is a finite time involved. From an experimental perspective, what happens if I want to perform a measurement of an observable which is not compatible, starting in the intermediate time when it has not settled to one of the eigenstates?
Yeah, you can do that indeed. So indeed, according to these collapse models, a measurement takes some time, can be quite fast or very fast, but it takes some time. And indeed, since it takes some time, you could, in the middle of that, start another measurement. And that would just be described by the same kind of stochastic equations. And of course, then it depends on all the details, but you can do that kind of things.
But in the middle, in the intermediate time, in the stochastic Schrodinger equation, the state is described by a statistical mixture of the...
No, not in the stochastic Schrodinger equation. The state remains pure. If you start with a pure state and you have this equation, like the one that was shown this morning, it's really for a pure state, psi, and you had an evolution equation for psi. So the state remains pure all the time. As long as you don't average over all the possible outcomes. Of course, if you average over the outcomes, then you get a mixed state. But if you just look at one realization, or it was one of my Brownian-like curve that I showed briefly, you had this moving thing. So this is Brownian motion in Hilbert space, but each of these curves corresponds to a trajectory of a pure state in Hilbert space.
Adrian, do you want to add anything to what Nicolas now commented upon?
You hear us, Adrian?
Adrian, can you hear me?
Okay. I think we just continue, and there will be questions which are more directly for...
Sorry, I can hear Nicolas, but I can't hear maybe the chair in the background.
Hello. So Adrian,
you hear only the important answers, but not the question.
So Adrian, do you want to add?
Do
you want to add something to?
No, I think the question was a technical point, and Nicolas, of course, I agree with Nicolas' answer. That's fine. Thank you.
Okay. So now there is Ripendo.
So, I am Nipendra from IIT Tirupati. So, I want to ask from Professor Gisin. So, in one of the slides you mentioned that information is encoded in the initial condition. So what is the criteria, means the very criteria to consider the initial condition? Because let's say for Schrodinger equation, if I take t equals to 0 time at initial condition is 0, it can be something else for means someone else. Cannot be t equals to 0 for someone else. For me it is t equals to 0, that is fine. So what is that very criteria to consider the initial condition?
Okay, not sure I fully understood. I tried to answer, but then maybe Adrian can indeed elaborate. So Schrodinger equation by itself is a deterministic equation. Newton equation by themselves are deterministic equation. However, then in both cases, you can interpret the physics as being indeterministic. For instance, the initial condition of the classical evolution is not yet fully determined because of the real numbers not being real, or in the quantum case, because indeed you are measuring an observable which is not compatible with the state on which you are measuring it. So you get some probabilities given by the Born rule. But indeed, for this deterministic equation, you need some initial conditions so that you can start computing, letting the system evolve according to these dynamical equations. I don't know, maybe Adrian, do you have did you hear the question?
But I'm not sure if I understand the question. Is the idea that there's a sort of perspectival view of quantum theory and different observers assign different states to a system?
So the question was, I think, about the status of initial conditions.
Yeah.
Yes, but Well, maybe the questioner can clarify. I took the questioner to be asking what happens if two different observers assign different initial conditions. And I'm not quite sure
Yeah, so
under what circumstances
so the
would,
question is
you
like,
want that to happen.
yeah, so question is like, let's say for I take some initial condition at t equals to 0, maybe something, if someone else, some observable is there, it can be something else for him it is. So what is the very criteria to choose that initial condition?
I see. So I guess on the sort of realist view of quantum theory that both Nicola and I, in our different ways, have been arguing for, there should be some fact of the matter about the initial state, and ultimately, hopefully, there should be some theory of the initial state. But in practice, we may not have access to either to the complete theory of nature. So different observers may use whatever information they have to give their best estimates of the initial state. I wouldn't say that causes a fundamental tension. It just means that different observers, because they're ignorant about some information about the system, end up making predictions that reflect that ignorance to some extent. So each observer is allowed to use their best estimate of the initial state and can infer probabilistic predictions from it. And in general, both of them know that their answer is not complete and not the best answer that could be obtained if they had perfect information.
Yeah.
Does that address the question?
Yeah, it's okay. Thank you.
It's basically
Somehow I understood, but
it's
not-
dependent upon the information accessible to the observer, to the person who is ascribing the initial state.
Okay, thank you. So I have another one. Maybe I lost at that point. So why do you need that non-linear condition? I lost at that time, so I couldn't understand.
Well, so if you stick to linear evolution equations, whether it's deterministic or not deterministic, but if it's linear, and you start from a superposition, let's say atom being excited, in a superposition of excited state and ground state, and then you couple it to, the famous cat or to whatever other object, by linearity, you're going to get that this cat or macroscopic object will end up in a superposition. That's just a consequence of linearity. You can add solutions. That's the meaning of a linear equation, that you can add solutions. And so just by linearity, you will have this problem. So we are looking for nonlinear solution, nonlinear evolution equations. And if it is a deterministic nonlinear equation, then you will have signaling. You can use the non-locality to signal, or you can activate non-locality, as we say. Okay. And that's the motivation to look for nonlinear and not deterministic, which means stochastic equations. And indeed, I mean, everything that we mentioned today, this morning and this afternoon, is always the same kind of equation, which is a Markovian equation, nonlinear of the same sort, and which the fact that it is nonlinear and stochastic doesn't yet guarantee that it is non-signaling, but the kind of equations that we consider it, these are special equations that are just the right form that we do not signal.
Okay, yeah, I got it. Thank you. And the last one.
Sorry, could I come on?
Yes,
before you go to the last question, could I come in on that point? So Nicolas did pioneering work indeed on the relationship between linearity or non-linearity and signaling. But as you'll remember, there is a loophole in his argument. So there are non-linear ways of modifying quantum theory, if one's careful about it, that don't imply no signaling and allow you to go beyond the Markovian collapse equations that have been central to the discussions this morning. And another answer, a different answer to your question, why would you look for a non-linearity? Well, two different answers. One would be, it seems actually very surprising that linearity holds perfectly true throughout nature. And it seems particularly surprising if you think about the interrelation between quantum theory and gravity. Quantum theory is a linear theory. General relativity is not a linear theory. It's possible that quantum theory just wins and general relativity gets broken down into a linear quantum gravity theory. But there's certainly a lot of motivation for thinking that things might go in a different direction, that the non-linearities of general relativity might be required as corrections to what we now think of as quantum theory.
Yeah, maybe
I don't know if I'm confusing the discussion or just, but I think it's important anyway to recognize that you can introduce non-linearities in quantum theory without no signaling. You just have to be careful about it. And this old work of mine and more recent debates with Luis Massanis and others on the archive that will appear in Quantum soon that addresses this in quite a lot of detail.
Okay. Actually, I was expecting that Adrian will say that, because indeed we have I wouldn't say a debate, but indeed I claim that any deterministic nonlinear Schrödinger equation would lead to signaling, and Adrian has an explicit counterexample somehow. But when it all boils down at the end, what do we mean by signaling? And signaling has really two different meanings. One is faster than light communication, and indeed Adrian's model does avoid faster than light communication. However, signaling has a second meaning, which I usually phrase as non-physical communication, namely that you could not communicate from A to B without some physical object, energy, particle, wave, or something going from A to B to carry the information. You know, information is physical, that's the slogan. And so information being physical, you cannot transmit information without some physical support. And in Adrian's model, if I understood it correctly, Adrian, you can communicate without any physical support, so it is signaling according to the second meaning of signaling.
That's absolutely right, and it's a key point. But I would say, you can think of the model as a sort of high order description of what might be going on at the fundamental level, and what could be going on at the fundamental level could indeed involve a signaling medium in that second sense, so something that's carrying the information from A to B, for instance, in the gravitational field.
But in this case, your model is not complete. There is something missing yet. But anyway, I don't think we should continue on that. But this is an ongoing little debate between Adrian and myself.
Yes.
Okay.
In the microphone.
What is the upshot, just to summarize to the audience, for the convenience of the audience? There are two different viewpoints.
So my claim is that any deterministic nonlinear Schrödinger equation leads to signaling, either in the sense of faster than light or in the sense of non-physical communication. And Adrian has an example which clearly does not signal faster than light, but also it stands today. The model allows for non-physical communication, and Adrian says yes, but it can be complemented.
It can be?
Well, I mean, that's what he says, and I don't know about that, and maybe yes, maybe no. But this is the situation today, and I don't think we should, we're not going to solve it in public in the 5 next minutes. This is something we're debating for 10 years at least.
The summary? Adrian?
I completely agree.
Adrian, do you agree with this summary?
I completely agree, yes. Yes.
Okay.
So I have the last question, sorry.
You had already the last question. That's
I have the last question. So, in one of the picture you said that how do you know? So, you said that the phases are getting constructively added. So, how do you know that whether it is getting constructive or destructive?
because I know experimental physics.
So let us.
I mean, this is when you have many antennas. If they emit at random, each of them, you will get a certain efficiency of emission. But if they emit in phase, in a certain direction, then you will get a larger emission in that direction. That's the way radio functions, ion functions, atom functions. It's even true for water waves.
But sometimes it might get destructively added also.
There are also directions in which they interfere destructively, indeed. But there is one direction in which they interfere constructively, and this will be by far the dominant direction of emission.
Okay, thank you, thank you.
Okay, now at this point, Howard is online, and he has raised a hand. He wants to
Hi, Howard.
intervene with a comment. So Howard, please go ahead. Do you have a comment? Hello.
Hello. Hello.
Hello.
Can I be heard?
You can. So do you have a
Yes,
comment on
okay.
this issue?
Yeah, well, since that was the last question, it seems like there's time for me to squeeze one in. So this is a question for both Adrian and Nicolas. So you both sort of objected to the term quantum measurement problem, but it seemed to be in completely orthogonal directions, in that Adrian didn't think it was about measurement, and Nicolas didn't think it was really about quantum. And that seems to be a big divergence. And I'm wondering if you could comment on where that's coming from, and presumably, yeah, whether you're also any closer to seeing eye to eye on this after many years.
Adrian, you should start.
Wait, to be precise, and as careful as possible, it's not necessarily about measurement. I mean, I think it probably isn't really to do with measurement. The solution to the quantum reality problem probably has nothing to do with humans or apparatuses or conscious observers. There is this line of thought that consciousness is crucial, and then maybe the quantum measurement problem really is a measurement or an observation problem. Is it to do with quantum? I mean, I'm still trying to sort of find my way into loving Nicolas' way of thinking about real numbers and classical indeterminism, and I haven't really got all the way there yet. So to me, it still seems very much as though the quantum measurement problem is a story about the incompleteness of quantum theory, and beyond that, the incompleteness of fundamental science. And we have clear. We don't know how to complete it, but we know and we may be wrong even about the form of the possible completions, but at least we have sensible ideas in the abstract about what the form of possible completion could look like, and various interesting research programs that are trying to produce a completion. I'm not sure if I'm answering your question or just recapitulating my earlier thoughts, but maybe Nicolas can shed a little bit more light on divergence.
Well, so I think that Adrian and myself don't disagree that much. We both are realists. We both believe that the world is out there and existed and was going on way before humans happened, and even less humans with PhDs and so on. Now, okay, for classical mechanics, indeed, you can interpret it differently, and maybe Adrian prefers to have the hidden variable real numbers. I prefer not to have them, but that's not so important. But I think we both agree that measurement-like processes, so actualization, happened already way before humans or living beings. And that's why I say that collapse, what else? I mean, collapse-like models, not necessarily one that is published today, but something along this kind of line that happens spontaneously. Also, when we say that it may have something to do with gravity, of course, gravity existed before humans, and so this is also not limited to human measuring devices. You have that also happening behind the moon. So I think that actually Adrian and myself, we are not very far on that. I'm sure you could find people on this planet with very different opinions. Just invite Lev Weidman, and then you get a very alive discussion.
Oh, yes. But there are many dimensions to be orthogonal in. I mean, yes, he just... so, yes, I don't know where that can go anyway. Anyway, thank you for your comments. I hope that that might be useful for the audience as well.
Okay, so we come back.
What's your take on the answer to your question, if I can ask?
Okay.
Oh well, it was helpful to hear your comments.
You should prepare your
I don't
answer
know
for your
whether-
talk of tomorrow.
Yeah. I mean, I guess the question for Nicolas is, would he have been if you had been born even earlier, Nicolas, and had not lived for to see the birth of quantum mechanics, do you think you would have been fundamentally unhappy with the deterministic physics that everybody believed in?
I'm not sure I understood the question. Whether I would have been happy with deterministic...
or whether you would have been unhappy with the deterministic classical physics.
You know, until, I don't know, 10 years ago, or probably more, I was quite happy with Newtonian standard mechanics because I didn't realize that we were using hidden variables and assumptions about infinite information. So I changed my mind.
So the realization that mathematical real numbers are not physically real is crucial to your transformation of thought.
Yes.
View.
Yes.
And on this point, I think Adrian disagrees, no? He does not consider
You
this
want
to
us
be
to disagree?
Yes. And what is your view, Howard, on this, about the indeterminacy coming from the infinitesimal digits?
Oh, I'm not going to commit to no. I just wanted to understand Adrian and yeah, where it was coming from. But I do think, I guess you both do tend to favor the idea of actualization then in place of measurement, maybe.
Yes, he suggests a solution to
right.
reconcile.
Let's go back to the young guys here.
Yes.
The future is there anyway.
Yes. So.
Oh, I thought I was just filling in times. I apologize if there are questions from the audience. I will bow out now. Thank you.
And tomorrow you can give your further comments on this. So let's move on. Now I request Shapta Sindhu.
Hello. I am Shaptashendra Pal Chaudhary from DRDO Delhi. So my question is to Professor Gisin. So in your talk you mentioned that what is mathematically real number are physically random number. So I wanted your elaboration on that. What do you mean by that? And I have one more question. So that is, since current mathematics is constructed by human, so does this limits the understanding of quantum mechanics since we use it in quantum mechanical calculations?
Okay, so two questions if I understand correctly. So when I claim that mathematical real numbers are random, this is not really my claim. This is something which mathematicians would also agree. No, the typical real number are numbers whose digits or bits, it doesn't matter in which basis you write the number, have no structure at all. If they would have any structure, you could use this structure to give a name to this number. And so every number that has a name or an algorithm, equivalently, is non-typical. And the number of names or algorithms you have is infinite, but it's countably infinite, while the number of real numbers is continuous infinite. So you see that you have infinitely more numbers for names, hence you have infinitely more typical numbers for exceptional numbers. And again, all these typical numbers, they must have no structure in their series of digits. Again, because if there would be any structure there, you could use that structure to give it a name. So this is not something, it's not my opinion. This is a well-accepted, mathematicians would also agree on that. So this is one point. Now the second one, mathematics is made by humans. Does it limit ourselves? I mean, we are certainly limited beings, no? Dogs don't understand quantum mechanics or don't even understand classical mechanics. We have the feeling we understand classical, but maybe not well quantum, and maybe superhumans will understand more, I don't know. But this, of course, we have to do with what we have, and we have one brain more or less of that size, and so on, and we can do quite a lot with that. Nevertheless, I think that's the models that we develop with that are pretty good approximation of the reality out there. So I think we can indeed approach this reality. We cannot reach it, but we can approach to it quite well, and that's what we do, we the physicists, or the scientists more generally. And to do that, we of course invent tools. And as I said repeatedly, tools are essentially stories, but then sometimes these stories, if you put them in very formal ways, in mathematical and axiomatic ways, they become kind of very strong instruments to understand how nature does it. They are just instruments, so it's not sufficient, but it's a very useful tool to understand nature. We couldn't compute the spectrum of the hydrogen atom if we wouldn't use mathematics. English words would not be sufficient. Does that answer your question more or less?
Okay, thank you.
Good. Adrian, do you want to add anything to that?
That's fine, thank you.
Okay, thanks. So, Arnab?
Hello, I'm Arnab Acharya from VNIT Nagpur. My question is for Professor Gisin. So you're very adamant about not giving up realism. And, so that we are on the same page, realism in the context of Bell's theorem tells us that all observables already have some values, just that we don't know. Am I wrong? Yeah.
Yes. No, realism doesn't mean that all observables have a physical value. You can be a realist and nevertheless think that you have indeterminacy out there.
Right.
Of course, some things really exist. I mean, these exist.
Okay.
And so on. These exist, and so on. So something exists, but there are many things that are in a state with some indeterminacy.
I see.
So for me, you have probabilities, and clearly the standard probability theory, the Kolmogorov ones, they are extremely well suited to describe our ignorance. They are made for that, and that's good. But you also have probabilities that are objective probabilities, and these ones do not necessarily satisfy Kolmogorov axioms. There is no reason that they satisfy them. And one example of possible objective probabilities are those that we encounter in quantum physics.
All right. And about your comment on numbers, if I take out the irrational numbers, rational numbers perfectly have finite amount of information. So would you be happy with that? Because it can also approximate any irrational numbers arbitrarily, closely.
Yes, but if you only have these rational numbers, for instance, then according to Newton equation, you can start with rational initial condition, you let it evolve, and at some point, very quickly, almost immediately, you will have non-rational solutions. So if you want to stick within rational numbers, or even if you want to stick within computable numbers, you can no longer use Schrödinger Newton equation.
Right. Thank you.
Adrian, would you like to comment on this? Adrian, would you like to comment on what?
Yes, just to reinforce Nicolas' answer to the first part, because I think this is absolutely crucial. Realists are absolutely not committed to saying that in general an observable has an objective value. They're committed to saying that sometimes some facts about the universe are true. So in the case of a Bell experiment, a realist account ought to say that the measurement outcome has an objective value. But as Nicolas highlighted actually in his talk, that still leaves the question, what was the measurement outcome? Where did the measurement outcome take place? And it may not even have taken place in the photodetectors where we normally think it took place. It could have taken place much later on. So the constraint on realists is to produce not a complete description of the possible outcomes of all possible measurements that would contradict Bell's theorem and many other things. It's to produce enough information to reconstruct some roughly classical description of the world of the sort that we see. Perhaps plus much else stuff, but the minimum criterion is it should there should be enough data that we can describe the sort of world that we actually experience. And that's a much weaker constraint than assigning reality to every possible observable.
Okay.
I think Nicola and I completely agree on this,
Okay.
unless Nicola wants to come in again.
Okay. So you would like to comment on this?
So respond, yeah. You know, you made a distinction between Kolmogorov probabilities and you called the quantum probabilities as the objective ones. I'm a bit concerned. Consider the possibility that underlying quantum theory, there is a deterministic theory which, when coarse-grained, gives rise to ignorance and hence probabilities, which I would call the Kolmogorov type and not the objective type, in the same sense like, say, in Brownian motion. Maybe there is a microstructure, which I'll talk about tomorrow, which is not being observed when, say, we make a measurement. For example, the time of arrival may need to be known, maybe, to the accuracy of Planck times. I observe it only up to, let's say, 1 second or microsecond. And in that duration, lots is happening. And if I could see that, I would know whether the outcome will be up or down.
I'm going to comment after listening to you. I cannot make a comment before hearing your talk.
No, in principle, would you rule out Kolmogorov interpretation of quantum probabilities?
Yes, but you know, because I don't believe we are hidden variables, at least not local hidden variables, nor deterministic non-local variables, as I emphasized yesterday. So I don't believe in that. So my answer, and you know it already, is just no.
Hidden variables are a different thing from an underlying theory, which is
this
more.
You're going to explain us tomorrow. So how can I tell you the answer now that I have not yet listened to your talk?
Adrian, do you have any comment?
We would like to wait for the talk to comment.
Okay.
Thank you.
Okay. So, Shourab.
So, hi, I'm Saurabh. I'm a PhD student here. So I wanted to ask a question to Professor Gisin. So you mentioned something about how if you could do a joint measurement on, let's say, 2 qubits, that would cause signaling, right? So, and then you mentioned something about joint measurements on larger number of qubits. Like, so could you elaborate on that a little bit? Like,
yes. So indeed, in the example, it was only 2. So in this middle region, you had only 2 systems, and in the example, even only 2 qubits. And then the statement or the theorem is that except for Bell state measurement, every measurement there would lead to signaling if you could describe it with the projection postulate. So not only going from potentiality to actuality with the Born rule probabilities, but also the post-measurement state would be described by the projection postulate. But of course, you can imagine quite easily just to add a 3rd party or a 4th party or any number of parties there. And then you have many more possible measurements. What I'm asking to myself, but to everybody here, you know, we know the Bell state measurement. We know also the so-called GHG measurement, which is essentially a kind of generalization of Bell state measurement for any number of parties and any dimension. So it's nice. But this is the kind of the only joint example of joint measurements valid for arbitrary number of parties and dimensions that we know. And on the other side, we know that there must be many, many more, because there are continuously, infinitely many measurements. So I think one research program, which I'm suggesting to you and all your colleagues here, is to find families of joint measurements. Let's say we could even start by limiting it to qubits, but more than 2 qubits, 3, 4, 5, whatever. And of course, I don't want just a random example of a measurement. Of course, I can use my random number generator and produce a measurement. But I want something that's a bit like this for the real numbers, but something that is computable. So something I can give a name to it, something I can describe. It has some symmetry, it has some elegance, it has some usefulness, and so on. you know, since the beginning of quantum information science, we learned enormously about entangled states, and not only between Alice and Bob. We could have Alice, Bob, Charlie, and they could have systems of high dimensions, and we have all kinds of Bell inequalities. There's a zoology of Bell inequality today. But entanglement also plays an important role in measurements. Just think of measurement whose eigenstates are entangled or whose POVM elements are entangled. And there, it so happens that we know almost nothing. And so I believe that there is a large and fruitful research program there. And I think it is not, of course, directly connected to the deep measurement problem, but it has to do with measurements. We need more than one example of joint measurements.
Oh, I don't know if I missed your point, but like, see, you could have, let's say, some collection of qubits, and you could entangle them to a particular ancilla, and you do a measurement on that ancilla. Depending on the choice of entangling operations you did, you could implement a whole range of possible measurements on those qubits, right? You have a continuous range of. Isn't this what you're talking about? You can do in many possible joint measurements like this. I mean, you could.
So if there are many possibilities, give me one.
No, these kind of measurements are done a lot in like error correction, where you do these stabilizer measurements. You do these joint measurements by entangling a bunch of things to one, and then you project that one out.
Okay, maybe it's just my ignorance, but I think it would be nice to have some examples, very explicit, kind of elegant, natural, maybe inspired from error correction. That's fine.
We can discuss more.
Yes.
Thanks.
Adrian, would you like to comment on that? Or about that joint measurement issue, about the examples of joint measurement? Nicolas talked about a joint measurement of two qubits which does not single the Bell basis.
Maybe I could add something on this, which is the discussion that Nicolas set out is intriguing, but it feeds into a maybe even deeper question, which is the nature of measurements in relativistic quantum field theory. And there's a lot of interesting recent work on this. You could take even what we thought was the simplest possible example. Suppose you want to take a charged particle in a two-slit experiment and separate the paths and then recombine them. And then first that seemed to create a paradox. If somebody some distance away from that is measuring the Coulomb field of the charge, then it seems as though they could tell which path the particle went along, depending on exactly how strong the Coulomb field looks to them. And then, at least at first sight, obviously you need to think harder, but at first sight it seems it doesn't really matter how far away they are. They should be able to decohere the interferometer. And then it shouldn't matter whether they're there or not. The possibility of carrying that measurement should be enough to decohere the interferometer, and so you end up with the obviously false conclusion that you can't do interference with charged particles. So a careful analysis of this, and there've been a whole slew of papers starting, I think, with Mari et al. In 2016, and then Bob Wald and collaborators, but I still think there's more to understand. A careful analysis tells us that even what we thought of as straightforward quantum measurements in relativistic field theory take a certain amount of time. If you try and do it too quickly, you can't do it, or you can't get the answer you expect because you will radiate away. So you have to make your interferometer relatively slow so that the radiation from the two paths is relatively negligible and they don't self-decohere. And there's two perspectives on that. So thinking about the radiation is one, thinking about the possibility of party over here carrying out a Coulomb measurement is another. But they have to fit together in the same picture. And I think we're a lot closer now in the last few years, but still maybe not completely all the way to understanding exactly how they fit together in the same picture. So I'd like to see a unified understanding of what exactly measurement is in relativistic quantum field theory. And these special cases where we're thinking of qubits as isolated, essentially point-like things are key ways of generating insight. but we probably really need to think about the full panoply of relativistic quantum field theory in order to understand the question in the generality we want to.
Okay. Okay. So Neelaj. Hello. Yes, Neelaj.
Hi. My question might not be exactly related to the content that was covered, but it is indeed in tune with the broader topic of the session. So yes, during yesterday's discussion, very briefly, the topic of contextuality, single particle thing came up, and a remark came up that that maybe non-locality is surprising, but contextuality isn't, merely because non-locality is something that's not quite intuitive, whereas contextuality seems intuitive. But to me, I kind of disagree, because contextuality seems to point at the quantum measurement problem, in the sense that the fact that measurement outcomes, they cannot be ascribed values independent of compatible measurements being performed, that kind of points at the innate invasiveness of quantum measurements. And also, I think briefly some correspondence was drawn between the measurement problem and how that is related to the Bell-type inequality violations. So I didn't really get that. So can you shed some light on these matters? Because I'm kind of in a mess in my head right now.
Adrian, we have a student who is in a situation of mess, so can you help?
On the issue.
So let's see. I suppose the intuition that contextuality might be a weaker and less surprising thing comes rightly or wrongly from the thought that we're bringing stuff right next to the quantum system we're measuring, and exactly the details of the apparatus, including what's the whole collection of measurements that it could be carrying out, can potentially affect the outcome of the measurement. So in a Bell-type situation, it's harder to run that argument, because it seems like if you try and run that argument, the details of the apparatus over here and over here both have to play a crucial role in determining what happens over here, and that conflicts with the spirit, and at the very least with the spirit of special relativity, and depending how you flesh out the mathematics, also with the actual postulates of special relativity. But I take your point that you can think of non-locality as a special case of contextuality. It seems to be one where there is an extra motivation for being surprised by quantum theory, at least initially. So the second part of your question was, I think, asking about these beautiful experiments that Nicolas described briefly, which turn again on this question of exactly when the measurement takes place in a Bell experiment.
Right.
I'm happy to say something about that, but maybe Nicolas wants to just comment a little more on those experiments first.
Which
You mean the experiments where we push this mirror with the piezo, this kind of thing?
Yeah, if I understood right, that was part of the question.
Okay, I didn't understand that this was the question. I don't know. You had a question about this experiment?
Right. So the first part of the question was why non-locality is more surprising than contextuality. Professor Adrian kind of touched upon that. My second part was related to the fact that last day, during the discussions, something came up where it was discussed that essentially Bell-type inequality violations can be in the end related to the quantum measurement problem. So what exactly is the correspondence in such scenarios? Because for me, the only way to look at it is through contextuality. Contextuality offers the approach where I can somehow think that measurement indeed has some invasive effect on my observation.
Okay, I think now I understand the question. Yeah, so in Bell inequality, like in device-independent quantum information processing, abstract everything to the statistics of these inputs and outputs. But the inputs and the outputs have to be classical so that we really can, do the statistics of these measurement outcomes, giving the measurement settings. And then the question about the outcomes, so for the inputs, when you can have the question, when are they really independent? How do we ensure that they are independent? But for the outcome, so coming to the measurement problem, for the outcome, you need to make sure that indeed the outcome, first of all, are classical, that you can publish them. Someone said that yesterday, that they don't suffer from the no cloning theorem, and also that they are really out there already. And so this raises the question, when is a measurement finished? Especially if you want to do this measurement in a space-like separated way, which makes sense, then you need to know the measurement now is finished and there was no time yet for any signal coming from the other side. But if maybe the measurement is not yet finished, it takes a bit longer, as we have, for instance, in this Joshi-Penrose model, but also maybe in some collapse models, it takes some time. And then possibly we believe it's finished, but actually it's not yet finished, and waste time for a signal at the speed of light to reach, let's say, Bob coming from Alice, and of course symmetrically. And so this connects indeed to this question, when is a measurement finished? And that's where I think it was really Adrian who was first to notice that if measurement take time, but significant time, not just a picosecond or a femtosecond or whatever, but it really takes time, then we have to be way more careful when we claim that we did a space-like separated Bell inequality test. And so that's what I showed in my talk, is that one way of, let's say, increasing the confidence that we do a space-like separated measurements is to let the detector activate a piezo, which pushes a little mirror, which was, I think, 12-gram mirror. Of course, it pushes it only 12 nanoseconds. Okay, maybe my numbers, I'm not sure, but you had the numbers, and so on. And then, because now you have something macroscopic, like this little mirror, that is pushed over some significant distance, certainly way larger than atomic distances, then you can build more confidence that in this experiment we really had space-like separation. So this is a connection to the measurement problem, of course. How long does it take to perform a measurement?
Thanks for. Okay, I think Professor Adrian wants to add something.
Thanks. Yeah, if I could add a little. So the way I would phrase this is, and did phrase it back 20 years ago, but it's still true. There is, despite claims to the contrary, there is still an important loophole in all Bell experiments to date. I called it the collapse locality loophole, and it's precisely to do with this point that Nicolas has been emphasizing. We don't know when measurements have actually been completed. We assume there is a fact of the matter about that, but it could be long after the point where photons enter photodetectors. The beautiful experiment that Nicolas describes was the first, and really, as far as I'm aware, still the only serious attempt to start to close that loophole. To completely close it, I think, and this will happen eventually, we're going to need to do a much longer range experiment, probably something like entanglement separated between, or shared between the Earth and the Moon, and have human observers on both Earth and Moon observing in real time the outcome of Bell experiments. And it takes long enough for a signal to communicate between the Earth and the Moon that even though humans are quite slow creatures to process things, assuming that we see things in the sort of time frame we think we see them, we could be confident that both outcomes are registered in space-like separated regions. So I would like to see that experiment done, and I know Yanwei Pan and other Chinese colleagues have in their long-range plans the ambition to do exactly that experiment, and then we can finally say that this particular loophole in Bell experiments has also been closed as far as one can possibly close it.
Right. Thanks for the insights.
So Adrian, you mean that satellite experiments should go further in the sense not dependent upon the specific collapse model being used. The experiment that Nicolas talked about, there you ensured space-like separation dependent upon what wave function collapse model you invoke, because you have to fix from theory what time it takes the measurement to complete. And for that you need a specific model of how measurement occurs.
So what Adrian is saying, let's go on to the point where it is a human that registers the result.
Then you are assuming
that the human will never get into a superposition state. So the human for sure will be completing the measurement. Of course, we will need a lot of PhD students to perform this experiment because we're going to become exhausted very quickly.
So is this what you are assuming, that by the human perception time the collapse should have occurred at that distance, satellite and the Earth, but the moon and the Earth? So
you're assuming that the measurement will be completed when a human registers the result.
And the motivation for that is, if that's not true, then all our attempts to resolve the measurement problem really start to lose motivation. You start effectively becoming an Everettian, even if you maintain you're not. If you think that humans can be in a superposition, and yet it appears that we have definite experiences. So that seems.
Harold,
like
are you going to do the experiment?
I do not think that it's necessary. You are a realist. You think that the world is there even if we don't measure it. I'm surprised now. You claim you are a realist and that the world is out there, whether we look at it or not. And still you want to see the outcome of the measurement result, otherwise it's not the measurement result. That, to me, somewhat contradicts now.
But I think what Adrian is just saying is that, how long do we have to wait? For sure not longer than it takes for a human to register the result. But of course, I think Adrian and certainly myself believe that it happens way before.
Yes.
Adrian? Okay. So next question is Shurajit Shah.
My question is for Professor Nicolas Gisin and Professor Adrian Ken. One possible view about quantum mechanics is that, of course, quantum mechanics is profoundly successful theory in terms of producing empirical results, but it does so operationally, leaving the deeper ontological questions that we expect from a physical theory unresolved. From this viewpoint, psi, the wave function, is a mathematical tool which encodes incomplete information about the underlying states. Somehow it encodes. Then, how much we can depend on psi or the evolution equation of psi such that we can modify it and solve the conceptual problems like measurement or others in quantum mechanics. And from this operational viewpoint, is it reliable to depend so much on the dynamical equation, that is Schrodinger equation, and modify the dynamics of that equation to obtain a real mechanism for collapse, like what we do in collapse model?
Maybe I start and Adrian will complement. So I think no one here pretends that quantum theory is the ultimate theory. So of course psi, the quantum state, is not the reality. It is a good approximation of it. However, within quantum mechanics, there is no more information than psi. That's the complete information according to the theory. Of course, there will be a post-quantum theory someday, and then we will have a better theory which gets closer to reality without reaching it, probably. So if we stay within this spirit at the level of quantum mechanics, you cannot have more than psi, and then the best we can say is how psi evolves. And that's what we do. Adrian?
Yes, I agree with that. I mean, what can we add to that? There are generalizations of quantum mechanics in which we could say at least different things about how psi evolves. So collapse models is one example. Time symmetric versions of quantum theory in which the initial and final states are separately modeled make different predictions, even though the Hamiltonian is the same. So I'm not quite sure what the question is pressing at. But I did want to pick up on one other thing that Nicolas said. Psi may not be a complete description or even a good description of the underlying reality. It's the best thing we have, and it gives us the best predictions we can make about what are in the end classical events that are all the information we have about the underlying reality. But it might be that in the underlying ontology, psi plays essentially no role. It's a mathematical object, but the ontology is written in a very different mathematical language. And so, some of the models that are in play have seem to be sort of pointing in that direction. I have this sort of feeling that I at least haven't really quite answered the spirit of your question, but I'm not sure exactly what you're pressing on. Can you elaborate a little bit further?
Actually, for example, some kind of model exists in the literature where wave function does not play any dynamical role. And that type of model is called emergent quantum mechanical model. And in that, from that point of view of that model, that psi, the wave function, is just something like a mathematical tool. Just like a complex number we use in AC current or electrodynamics, just a mathematical tool. And it predicts the empirical results of the experiment operationally. But leaving behind the important ontological questions like what a measure device is made of, or what a measurement device is made of, and what is the interaction between them. So, my question is, can we depend so much on psi or the dynamical equations of psi such that we can modify the equations and claim to solve the problematic issue of operational quantum theory?
Thank you. So I think I could say something sharper then. So an example where the ontology is not necessarily anything to do with psi would be Bohmian mechanics. There's more than one way of thinking about Bohmian mechanics, but at least in one way of thinking about it, psi is exactly what you just described. It's a mathematical tool, but the ontology is really the particle trajectories. And what your experimental apparatus are made of are, at least on a naive view of Bohmian mechanics, point-like particles that are following definite trajectories. And if you want to go beyond standard quantum theory and standard Bohmian mechanics, I think your question becomes a very live and important one. You can try and modify the equations of motion for psi. That's one way to go. But another thing you can try and do is use this extra structure and modify the equations using properties of that extra structure. And then, so something like this, that the evolution of a Bohmian state depends on the configuration of particles at a given time as well as on the state psi. So you're likely to produce sort of anomalous effects, including fast light signaling, unless you're very careful about how you do that. But you can do that. And that's the direction I was trying to push in the last part of my presentation. Once you have any ontology that underlies psi, you have a whole new set of strategies for generalizing quantum theory that use the mathematical features of that ontology itself and change the dynamics, not by changing the equations of motion for psi directly, but through rules that involve the underlying ontology. Okay. so I completely agree with the point of the question. There's nothing wrong with equations that are modified equations that treat psi only, but they're not the only option out there, and they're maybe, to my mind, not the most interesting option out there either.
Okay.
This may be a minority view, but at least right now the two of us share it, so that's good.
Thank you.
Thank you.
So now we move on and go to Archana.
Hi, I'm from ISER Mohali. So my professor is to, my question is to Professor Adrian. So when you talked about solution of this quantum reality problem, you talked about constructing a sample space of different configurations and then assigning a probability distribution to it. So first question is, what exactly are these different configurations? And then, so my understanding of probability theory is that you are essentially making some guesses that what are the chances of getting this outcome or that outcome. So for that you require an ensemble, or you are going to conduct experiment for a large number of times. So what if I say that no, you can only run your experiment only once, or you can only make it only on one copy of system? So can I ask a question like that in this framework? And if not, why not? And if yes, then how would you interpret your proposal? So that's my question.
Thank you. These are very good questions. The first one was about the structure of what makes up the configuration space. What are we actually talking about? If I understood right, and that I was deliberately uncommitted there because we don't know how to go beyond quantum theory. We don't know the underlying ontology. We know examples, so it's a toy example, but just as I was saying in the answer to the last question, Bohmian trajectories would give an example of something that you could apply these generalized rules to. The centers of collapses in dynamical collapse models, you can imagine rules in which the geometry of the centers of the collapses gives you an additional constraint or an additional rule for the probabilities. Any realist ontology gives this opportunity, and we're not in a position to say what the right realist ontology is at the moment, for better or worse. And the moral I would draw from that is that we should certainly pursue interesting lines of thought that we know are out there, including dynamical collapse models, but we should be looking more generally agnostically for any deviation from quantum theory. And cosmology is the most natural place to look for that. It doesn't really matter whether it's collapse centers or particle trajectories or something to do with events in regions. If there's a significant modification of probability rules that's detectable anywhere, it should show up in the end in cosmological data. So I'm trying, this is a slow process, but I'm trying to build a coalition of the willing among cosmologists who are willing to entertain this idea and search systematically for potential violations of quantum theory within cosmological data. And your second question was about one-shot versus many-shot experiments. So, actually, a more nuanced question than people sometimes give it credit for, because in science, we could think of a repeated experiment. We could think of a million experiments that seem to have basically the same initial state. Either way, I mean, in one sense, it's a million versions of a single experiment, but it's also one run of a complex experiment that involves a million different measurements on a system. And if we're testing any probabilistic theory, including standard quantum theory, we have to be able to look at it from both perspectives, because what we're actually saying, if we say quantum theory is confirmed, is something like this, that we did 1 million experiments and the Born rule predicted probability half that we saw spin up. And what we actually saw was something quite close to 500,000 spin-ups and 500,000 spin-downs. And that we take as confirmation of our theory. So we get into deep waters in sort of interpreting the foundations of probability in science. But I think Kolmogorov complexity is our way to navigate out of these deep waters. So a way of recasting that is to say we have no better way of explaining these data that's roughly 500,000 spin-ups and roughly 500,000 spin-downs than a model that starts with a completely random, incompressible random string and says the data will be essentially a completely incompressible random string. If there was a model out there, it should be compressible. If there's a model that says actually these experimental results corresponded to whether the corresponding digit of pi was even or odd, we could write a much shorter program that doesn't need to write a 1,000,000-digit string, but just works out the digits of pi, and that would describe the answer, describe the experimental results. So I don't know if that's helpful. Even if it's helpful, I don't know if it satisfies you, because people have very different views on the foundations of probability. But that's my sketch of how I think about these things. Maybe you'd like to come back.
No, all right. Thank you so much.
Nicolas, would you like to comment?
Okay, my pleasure.
So, Prem Kumar.
Hi, my name is Prem. I'm from IMSC Chennai. My question is to both the speakers. If we assume that we only have a global unitary for the entire universe and that there is no collapse, and if we also assume that the position operator is a special preferred basis, then will it solve the measurement problem? Because no.
Well, my answer is very simply no. But anyway, it's not very useful, because if everything is unitary, what I'm just saying is just a consequence of some quantum fluctuation at the Big Bang, and so there is no information content in what I'm uttering now.
Basically, the state will evolve through a unitary, and then we have this preferred basis based on which we can have the probabilities bound rule.
Yeah, but so you're asking me whether a purely deterministic world would solve the measurement problem, and I'm just answering that I cannot even give you any meaningful answer, because everything I could do and everything you could do, so your question also is just the consequence of a fluctuation that happened 13.7 billion years ago.
But we still have the Born rule, so probabilities will be there.
No, we don't have the Born rule. We are just the consequences of this fluctuation that happened 13.7 billion years ago. I don't know if you find that satisfactory. I think there is zero explanatory power in determinism, in pure determinism, only determinism. I have nothing against having some determinism. If I drop this thing, it's going to fall. That's okay. But to think that everything is deterministic is, according to me, has zero explanatory power. Adrian?
Yeah, so if I understand right, I think what you're describing is some version of many worlds quantum theory, or at least some attempt at a version of many worlds quantum theory.
Exactly.
And you're saying something like this, that your ontology is given by maybe psi, but more precisely by mod psi squared. So we have the full unitarily evolved quantum state, and within that we have some, let's call it a branch, which has some non-zero mod psi squared, which happens to be the branch that we're living in, and lots of other branches where different things happen. So my answer is also no. I don't think this satisfactorily resolves the measurement or reality problem, because I don't think there's a satisfactory explanation for the appearance of probabilities in such a theory. It doesn't look to me as though I'm spread out among these branches. It looks to me as though I see one event and then another event, and these satisfy the Born rule. And as Nicolas saying, you've described a purely deterministic theory. So even trying to frame a statement in which the word probability gets into your deterministic theory takes a lot of work. And along with that, you've got to talk about the problem of structure. So what exactly is the form of these branches? So we'll say, there are noble attempts out there by many people. I listed some of them, I think, on my slide. And I would also say, perhaps we should be humble. When there are many thoughtful people on one side and many thoughtful people on another side, I don't want to say that my side is absolutely certainly unquestionably right. But I can say I've tried my best to engage with the other side, and I'm not persuaded by any of their attempts at solution. And I gave some reasons in. I'm not sure I actually put the book up on my slide, but there's a book called Many Worlds ? Which I helped co-edit, with quite a lot of arguments on both sides of the many worlds. I gave some of my reasons for not believing in many worlds in that book. And final important point here. I mentioned the problem of probability. I mentioned the problem of structure, but there is also, I did say this briefly when in my presentation, the problem of scientific confirmation. Many worlds theories say anything could happen. What will happen next? Anything could happen. It's very, very hard. I mean, I'm being a bit glib about this, but if you try and be precise about it, it's very, very hard to see how you can end up getting evidence for or against such a theory. You do an experiment, something happens. Well, the theory says, yes, sure, that could. I told you, anything could happen.
But we have an extra. We have a preferred basis, let's say position, which we are calling postulating is a preferred basis. Using that, we try to derive the probabilities. Will that not?
Yeah, but still, all your preferred basis is going to do is tell you you're going to see things that can be cashed out in position space. So your pointer could be here or here or here. You do the experiment, you see the pointer here, and the theory says, yeah, sure, I told you the pointer could be anywhere. So I haven't really got time to go through all sort of first principles methodological discussion. But I think there's a profound issue in scientific confirmation of many worlds theories. And again, I disagree with some thoughtful people here, but that is not there in one world's quantum theories. And that's why, as a scientist, I want a one world theory.
Okay. My last question to Professor Gisin. Oh, sorry.
Hello, yes.
Adrian, could I respond and ask you a question? My name is Tejinder Singh. Suppose I say that there might be a deterministic non-unitary theory underlying quantum theory. I would like to say that that can be a one-world theory different from many worlds. Would you agree with that? Non-unitarity is the key. Deterministic non-unitarity need not be many worlds.
In principle, obviously, I would like to understand the details to see whether it's a theory that should be on the table or not, whether it has the other properties we want for a solution to measurement problem. But to the statement you've just given, sure, it doesn't have to be a many worlds theory in principle. We need to know more about the non-unitary dynamics to be able to decide on that even, I think.
Okay, yeah, thank you. Yeah, just wanted to ask you that. Yeah.
My last question to Professor Gisin. Can I ask?
Be brief.
Yeah. So there was already, this question was raised, but I have a follow-up on that. So if we limit, in classical mechanics, if we limit ourselves to discrete mathematics, rather than continuous mathematics, so we'll not have real numbers. And then consistently we can do this without encountering real numbers, like in, let's say, in coding, Python program or something like that. So then we'll not have hidden variables in classical mechanics. But similar trick will not help us solve the hidden variable problem of quantum mechanics. So do you think the hidden variable in quantum mechanics is fundamentally different from those in classical mechanics according to your work?
Yes, it's different because in classical mechanics, so you have indeed these real numbers as hidden variables, but these ones are non-contextual. While in quantum mechanics, if you insist to add hidden variables like Bohmian mechanics or whatever, they will have to be, non-local, we know, but they would also have to be contextual. So this is a big difference. And this comes from the fact that in quantum mechanics we have incompatible physical quantities. And the existence of incompatible physical quantities actually is really characterized by h bar having a strictly positive value. And we know that in classical mechanics we don't have any h bar, or we can say h bar equals 0, whatever. But that means that everything commutes. And so the variables or the physical quantities are all compatible, and so you may have non-contextual hidden variables.
Thank you.
So we come to the last comment by Professor Manobendra.
So there are two last ones apparently. So there are many last ones. Many worlds and many lasts.
Thank you for the discussion. Some of the questions have been asked. So I have two questions, first of all. One particularly for Gisin and for another one is for both of you. So first one is, when you talk about, let's say, this initial state definition or number assignment problem, obviously I understand that there are many possibilities. If I go down towards the digit further from the decimal point, obviously things will change. But determinism is not about that, no? Determinism is more about the laws. Any value you come up with, and my law will say for that particular value, it will give you a definite other value, which is the final one, no? So I still don't understand the motivation for you to doubt on this determinism. Second, which goes for both.
Let me answer the first one before you go, if not I get confused. So indeed the equations are deterministic, but if you apply them especially to chaotic system, but actually it's true in general, but especially for chaotic system, very quickly it is a not yet determined digit which will become very important, become the dominant digit, let's say. And so as you let your system evolve according to your simulation or to your theory, at some point you will need these digits which initially had no determined value. So you need to assume that nature is going to determine the value of these digits as time processes. And that is what brings in stochasticity or non-determinism, although the equations, again, are deterministic.
Okay, thank you. And the second question, possibly it's for me to digest further, because what I understand from all this discussion is that you prefer realism because you want to motivate yourself as a physicist so that you can continue doing research. I don't see, it looks like that, well, what is the point if I do away with realism? Rather, I'd be very happy to, because I see many things random, I would be happy to give up, let's say, determinism. Is this the reason possibly on which you are?
Well, you know, when I started physics many years ago, my goal was to understand nature out there. And so if not, I would have done psychology or something like that. But my goal was not to study humans, or my goal was to study outside reality. And of course, it doesn't make sense to study outside reality if you don't believe that outside reality exists. So this is the basic thing. And then there is indeed always this confusion between realism and determinism. So I'm a realist, Adrian is also a realist, but this has nothing to do with determinism. You know, so for some people they say, okay, realism means that every physical quantity has a value, and that measurements or all what we do is to reveal these pre-existing values, so everything is deterministic. But there is really, so I think in the mind of many people, there is a confusion between determinism and realism. And so that I emphasize on the very first slide We should not give up realism because we still want to understand how nature does it, nature out there. But we have to give up determinism, okay, for many reasons. One is Bell inequality violation, but you have more arguments. At least I believe in quite some arguments that determinism is not even an interesting position because it has zero explanatory power. Although I agree that is a kind of logical possibility, like solipsism is a logical possibility. You have many logical possibilities that are just not interesting, at least not interesting to me.
Okay, thank you. What is your take on this particular question, Adrian?
So, I mean, I completely agree with Nicolas. I'm a realist. I am not a determinist. There's absolutely no logical or aesthetic reason why realists should be determinists. If you really are a determinist, you have to believe that the precise state of the world right now was written into the initial conditions, and that's unless we're missing something. That means the initial description of the initial conditions is incredibly long string. It's incredibly complex. So I think if you want an elegant theory, you better not be a determinist. You better accept randomness in nature, and then we can understand. In principle, I mean, it may not be true, but at least we have the hope of understanding that simple initial conditions plus relatively simple evolution laws plus randomness can produce the marvelously complex world that we actually live in now. And your other question, are we just making work for ourselves as physicists? I tried to say this already in my talk. I mean, would you say that about people who tried to unify gravity with quantum mechanics or trying to produce a unified field theory? There is physics is incomplete. There's work out there for physicists to do. Of course, you don't have to be a physicist, but if you're a physicist, you'd better work on an outstanding physics problem. And the reality problem seems to me at least as pressing and compelling and interesting as the other two that I just mentioned. So that's why I keep spending quite a lot of time on it.
Thank you very much. Thank you very much.
Pleasure.
Yeah. First of all, thanks to both the speakers for patiently taking so many questions. So my first question is to Professor Kent. So when Weinberg gave his deterministic nonlinear equation, there are three criticisms comes. One's from Professor Nicolas Gisin, who have shown that it violates signaling. Another is from Perez, Asher Perez, who shows that it violates the second law of thermodynamics. And another is also from Polchinski, who shows that instantaneous signaling between different branches of wave function. Now you are saying that there are ways you can come up with a deterministic nonlinear differential equation which doesn't violate signaling as Professor Gisin is showing. What about the other two criticisms in your model?
Thank you so much for this question. Yes, the thermodynamics question is a really interesting one, and various people have asked it. I mean, it really goes back to von Neumann, but you're right, Perez then wrote a lot more about this. And I'm hoping to complete a paper with Samuel Fedida, a collaborator of mine, on this. But long story short, you don't break the third. You need to think what the second law of thermodynamics should actually look like in the context of nonlinear theory, and if you account for things correctly, you don't break anything, you don't get any paradoxes, you don't get any perpetual motion. Where you go wrong is if you take the standard notion of von Neumann entropy and apply that in a context of a nonlinear evolving quantum state. You do those two things together, you run into violations of thermodynamics. But the standard notion of von Neumann entropy is no longer the right thing to apply in nonlinear quantum mechanics, so you better do it better. Polchinski, so I have a confession to make. And partly because understanding what anybody says about many worlds quantum theory is kind of hard and it's often not very formulated. I never got precisely, I could never satisfy myself that there was a precise, rigorous statement that Polchinski was making about nonlinear many worlds quantum theory. But in any case, I don't think I need to worry because I'm not an Everettian, and I'm not going to be a sort of Everettian in the context of nonlinear quantum mechanics anyway. I imagine if we have nonlinearities, we also have some form of collapse, and so we don't have all these multiple branches, and so the issue of communication between branches isn't going to arise. But I would love, Polchinski was a very careful thinker, of course. I would love to get absolutely straight what precise statements can be made. I just feel even after all these years, I haven't got there yet. Okay. If you have, please message me and we can chat offline.
Sure. Thank you for answer. So my next question is to Professor Nicolas Gisin. This is a little bit more about philosophical because the discussion is like that. So in your slide, this realism, you said the world must there exist and function independent of human. So now I see this statement is a philosophical category. Neither I can falsify, nothing I can do. Because if I can do any experiment, whether independent of that, human will come. So it is a philosophical stand, and of course I also like to take that stand. It is a very rational stand. But now sometimes I find that, okay, some of my students ask this question, that okay, as a physicist, really world exists, but we are trying to give a description of the world and we are part of the world. So now if it happens that our description becomes, we become part of the description. So in a sense, our description becomes subjective. Means for Wigner, description is kind of one thing, for Wigner friends, description is different. So there is subjective, objective, that debate is now coming. So how you will see that things?
Yeah, so first I agree that of course realism is a philosophical position. The way I describe it is not super deep philosophy, but it's the pretty standard probably view of many physicists. And to the second part of your question, so indeed I never worked on Wigner's friend and all this kind of stuff, because I just don't think that unitarity applies to humans, to me, to you, or to anyone in this room. To consider a situation in which a human brain is entangled with a spin 1/2, although of course I can write that down on a piece of paper, but I don't think that has anything to do with physics. And so I don't, personally, I just don't want to spend my time on that. I have nothing against that people do that, and I have friends doing that, Renato Renner, for instance, and many more. Nothing against friends doing that, but I'm not going to do it myself because indeed I don't believe in the relevance, in the physical relevance of entangling human brains with whatever.
But it is not only about Wigner friend, but also this quantum Bayesian approach, what they are trying to say that the description becomes subjective.
Yeah, so yeah, so I don't know. Don't report that to Chris Fuchs, but you know, this cubism for me is no longer physics. This is very close to solipsism. So I'm not saying it is not consistent, but this is not the kind of activity I'm going to spend any time on.
Thank you. Thank you.
Adrian, do you have any comment? Adrian, do you have any comment?
You have something to say about cubism?
No.
Good, thank you for the answer.
So actually, we have overshoot the time by half an hour. Okay. So we have to close. You may talk with him, with Nicolas personally, and ask the questions. Just a point. Professor Ghosh, do you have any comment or no? You can discuss with. You can discuss with And do you have any question for Adrian? Because Adrian, you won't be able to discuss.
Yeah, I had a question
you have a
for
question
him,
specifically for Adrian.
Yeah.
So you.
Thank you. So I have a question primarily aimed at Adrian, but maybe even if Nicolas has a comment, I'll be happy to learn. But this is a question about not necessarily the measurement problem, but Bell non-locality. So if we believe the results of the Bell inequality tests, and if we accept that non-locality is inherent in nature, there's also this question of how much non-locality is actually allowed. And there's one constraint on the Bell parameter that it has to be less than 4 to respect causality. But there's another constraint which seems to come from entanglement monogamy, which is that not everything can be entangled with everything else maximally. So there are constraints on how the entanglement can be shared between different parties. So I was wondering if you could comment on the significance of entanglement monogamy for questions surrounding non-locality. Thank you.
Gisin may actually be much more of an expert than me on this. So the first part of your question, you're referring to really Popescu-Ehrlich boxes, which highlights that the algebraic bound and saturating Bell inequalities is 4. The quantum mechanical bound is 2√2, and that's only attainable if you have a maximally entangled state, and so you have no entanglement with any third system. And there's been a question that was really thrown out by Popescu and Ehrlich that people keep pressing on. Why does nature stick at 2√2, if indeed nature does, rather than going further towards 4? I don't know. I mean, one answer to that is perhaps we should think about whether there's a fully fledged dynamical theory that incorporates PR boxes, and I haven't really worked on this, but my understanding is that there isn't. Nature actually wants dynamics and wants to be able to allow arbitrary systems to interact, and maybe quantum theory is, and the quantum bound is as far as you can get with that. And this is it's a natural way, because at least historically, of calibrating non-locality to use CHSH violations, but it's quite an arbitrary way. There's nothing particularly magic about the CHSH inequality. Something that I've played around with, for instance, is if you wanted to measure the non-locality of a singlet, you can ask how anti-correlated are two measurements that are separated by a given angle, and that gives you not just a number but a function, a functional dependence on theta. And then you could ask, is there something like a PR box that is more non-local than quantum theory? But now what does that mean? Well, that presumably would have to mean a function that is everywhere gives a stronger anti-correlation than the quantum function. And the answer to that is no. There is no such function. So it's not even clear to me that if you think about it in terms of other natural net metrics, that there is something more non-local than quantum theory, even algebraically, out there to be discovered. I'm not sure I have much. I mean, you're right, of course, that the monogamy of entanglement plays a crucial role in the theory of non-locality. I don't think I have much more to say about that than the obvious. Maximally entangled states, by standard measures, but not by all measures, are maximally non-local. And if you use other measures, well, things get rather interesting, and there's a very interesting interplay between multipartite non-locality and multipartite entanglement, which I haven't really worked on, but I believe Nicolas has. So maybe I should hand over.
I don't think I want to add much more on that. I think it's already quite late, but we can discuss more about that later.
Thank you.
Okay, so.
Sorry, yeah, thank you. My last question.
No.
Yeah.
Hello.
Yeah, thank you. Sir, my last question is for Professor Gisin. It's a really small question. It's not at all on the philosophical or subjective side, but it's on the slide that you presented on the Gedanken, where signaling is not consistent with the axiom of projection onto the eigenstate. You had your receiver and the source such that their light cones were not intersecting, but you had a measurement, spatially extended measurement in between, which acted as a source of the communication between the source and the receiver. My only doubt was that everything was fine, but the entire thing rested on the fact that the receiver can distinguish between the zero state and the plus state. Could you kindly explain how could the receiver finally distinguish between the zero state and the plus state if he's not having an ensemble of them, but just a single qubit is going?
Well, he would measure in the computational basis, and whenever he finds a 1, he knows it was a plus state, because it couldn't be a 0 state. So you're right, you cannot deterministically distinguish the plus and the 0 state, but you can distinguish them probabilistically, and that is enough for communication. It would be a communication with less than 1 bit per instance, but you still have a positive rate of communication.
But since it was not an absolute deterministic evaluation,
but you don't need, I mean, if communication would be restricted to deterministic one, then you could never communicate, because in every communication you have some noise, so there is always a probability of failure. And despite the existence of a probability of failure, we can communicate. That's what we are doing presently. That's what you're doing when you send emails and so on. So we know how to deal with errors. That's okay. Important for communication is that you have a non-zero probability that the message or the information, the bit in this case, arrives.
So
that's sufficient.
There is a 50% probability that he will not be able to distinguish if he gets the zero state.
Yeah, but if there's a 50% probability that he distinguishes, that's good enough.
Okay. And a small last thing, this is transferring information at a superluminal velocity, but any physical field is not getting transferred at a superluminal velocity. So are we concerned about this?
You're right. This is superluminal communication, signaling in this sense. And it is really coming from the fact that we have described this measurement in this extended middle region, applying the projection postulate. And it is really applying the projection postulate that causes this signaling or this impossible measurement.
Thank you. Thank you.
Okay, so we come to the end of this session, and I invite Professor Banerjee to say a few words. Thank you. Thank you, Adrian.
Thank you. Yeah, it was really a very illuminating session. Now it is my pleasant duty to give the memento to the speakers.
Thank you. Is it the same as yesterday? Thank you.
There is a present for...
Here.
There is a present for Adrian also, but he will have to come all the way to our institute in order to receive it. Or it will require a superluminal communication.
Thank you.
It is poster session time now after the dinner. Yeah, let me just announce that tomorrow, just before the lunch, there will be a photo session. So everybody has to come to the photo session at the same time. So don't start taking lunch before time.
Bye-bye, Adrian.
Bye.
Bye. Thanks very much for the discussions.
Yeah, bye also, Francesco.